Good evening, everyone, and a very warm welcome to Physics for Students. Well, every journey in science has a story, something that starts, the story begins exactly where you expect to, and sometimes it takes a completely unexpected turn. Well, today's guest is someone whose journey beautifully reflects that spirit of curiosity, courage, and intellectual dedication. He began with mechanical engineering at IIT Madras, but somewhere along his way, his curiosity pulled him towards the deeper questions of theoretical physics. That journey eventually took him to Arizona State University, where he pursued his PhD in string theory under Professor Maulik Parikh, whose own PhD observer was Nobel laureate Frank Wilczek. But the story doesn't stop here. During his PhD, he explored quantum mechanics as a side project with Paul David and Yakir Aharonov. He later joined ICTS Bengaluru as a postdoctoral researcher working with Professor Subrat Raju. And remarkably, at a very early age, he took up a faculty position at IIT Indore. Now, those achievements reflect not only his exceptional talent, but also his perseverance, humility, and deep commitment to understanding the fundamental laws of nature. His journey is an inspiration to students and young researchers who dare to follow their curiosity beyond conventional paths. Today, he is an associate professor at BITS Hyderabad, where he continues to explore the fascinating world of theoretical physics and to inspire the next generation of physicists throughout his teaching and research. Well, yes, I am talking of Professor Prashant Samantray, whose remarkable contributions, intellectual curiosity, and passion for physics have made him a respected and inspiring figure in this field. Sir, a warm welcome for Physics for Students and a welcome to our podcast.
Thank you very much, Shonak, for that wonderful introduction. And thank you very much for this opportunity. And it's a pleasure.
Thank you, sir. Thank you. So, what we were going to do today is that because Prashant sir is there and he's an expert in the area from quantum mechanics to quantum field theory, string theory, and certain parts of gravitational physics also. So, we will start a journey where we can actually learn certain things from him. So the questions that I would be asking will actually inspire us and make us learn from certain objects. And also it is a kind request to all of you that relevant to what we are discussing and otherwise you can ask questions and I'm going to take it from time to time. Sir, first of all, what I would like to know is that when we talk of quantum mechanics, I would like to know because you have been, working both in national and international frontiers. What fundamentally is quantum mechanics a theory of? Is it a theory of reality or a theory of our knowledge about reality?
Okay. So I have to look at quantum mechanics as a framework. All right. I mean, in fact, most of our theories are frameworks, including quantum field theory or even string theory. So it's an exceptional framework. I should be very clear about that. And within its domain of validity, we have not observed any deviations from its predictions. And the rules of quantum mechanics seem like kind of a black box. Okay, we don't understand why the rules are the way they are, but they seem to be able to predict reality to a very, very high degree of accuracy. So, in a nutshell, quantum mechanics happens to be a framework which predicts reality to an extremely high accuracy. So there has been some work, to my knowledge. I'm not an expert on the foundations of quantum mechanics per se. I mean, I don't work on the foundational aspects of it. But I remember attending a workshop way back in 2011 when I was a grad student at Arizona State University. And there was this discussion about whether the wave function in quantum mechanics, I mean, we're talking about just normal non-relativistic quantum mechanics, whether the wave function has any kind of a physical reality associated with it. But if you carefully look at the postulates of quantum mechanics, then as many of the students might know about this, that every physical reality corresponds to some kind of an observable. And observables in quantum mechanics are associated with a one-to-one correspondence with something called a self-adjoint operator. Okay. Why self-adjoint operator? Because the eigenvalues has to be real so that you can observe that in the lab, and so on and so forth. But the wave function by itself, it's a complex number, and it's not self-adjoint. I mean, if I take what you call a Hermitian conjugate of it, it's not going to give you back the same object. So in that sense, it does not correspond to something real as far as the postulates of quantum mechanics goes. But as I was mentioning in the workshop that I had attended, there was a lot of discussion about it, that maybe one can give a physical interpretation to that. Not just interpretation, I mean, ascribe a physical reality to that. But it involves a lot of hidden variables and a lot of other assumptions that has to be put in, and maybe the Schrödinger equation itself has to be modified. So there is still a lot of debate whether the wave function or quantum mechanics, is it a framework or it actually exists in reality? Okay, but as far as I am concerned, as a practitioner of quantum mechanics or quantum field theory, I would look at it as a framework. So it's more about a toolbox, and it has a set of rules, and you follow those rules, and then it is able to predict reality to an extremely high accuracy. Whether there is another fundamental theory from which quantum mechanics follows, that is not clear yet. We don't know the answer to that. That's a deeper question. Yeah.
Thank you. Actually, I don't know, but you actually answered my immediate next question, which I was thinking, that what is wave function physically? Is it something that exists in nature, or is it just a pure mathematical representation? Okay, fine. So we are still in the debate. Okay, we have got a question coming up, a kind of an advanced question before we go to that arena. But anyway, we can take it. So, sir, this is the question A. Saxena is asking. Question for Professor Prashant. Can you please explain what is the ultraviolet cutoff in quantum field theory?
Okay, all right. Okay, so from quantum mechanics we straight away go to quantum field theory. So so the answer to that in a nutshell is basically, when in quantum field theory we are generally interested in computing quantities which explain something called scattering. All right, and not just scattering, we are also interested in asking questions like, okay, what happens? How does quantum field theory look like when we actually go to higher and higher energies? Okay, so what was quantum field theory like at the beginning of the universe, or closer to the Big Bang, whatever? Okay, so basically high energies, and it turns out that when you push the limits of quantum field theory in terms of energies, there seems to be some kind of a breakdown. All right, you cannot continuously push it to like all the way down to like extremely high energies, or technically speaking Planck energies. Okay, we believe that quantum field theory as a framework breaks down. Now, when we say about ultraviolet cutoff, we generally basically what we say is that, okay, when we are interested in understanding the low energy effective field theory, that means there is some kind of a fundamental theory at the high energy, but we are interested in the low energy effective limit. Okay, so that's, in order to do that, we have to put a cutoff. Like, it's basically a cutoff, like beyond that energy scale, I don't know what is happening and I don't care about it, but quantum effects are all included in that, and I am going to look at the theory from a slightly lower energy scale. So you zoom out. Okay, so the point at which you place that energy cutoff is basically the ultraviolet cutoff. Yeah. So if you ask what is the absolute hard cutoff, it's basically Planck energy or Planck length in that sense. Yes, that's where quantum field theory reaches its limits. Yeah.
Its limits. Okay. So, Mr. Saxena, I think that you have got a kind of a answer to that. Again, he has got a quick question. A following up question: does string theory tackle this problem of QFT breaking at higher energies?
I kind of anticipated that question. So a very quick answer: in quantum field theory, you don't need an ultraviolet cutoff. That's the beauty of in string theory, you don't need an ultraviolet cutoff. That is, I mean, the very fundamental formulation of string theory, because it assumes that you are not dealing with particles anymore, you are dealing with strings, which are basically one-dimensional objects. Okay, so when you deal with quantum mechanics of one-dimensional objects, you do not need an ultraviolet cutoff. So it's in that sense you don't need a renormalization kind of a structure in string theory. It's not there. It's not required. Yeah.
Right. Now, sir, as you know, that I continue producing videos for the students and for the understanding. Now, what I found it interesting is that the marriage of special theory of relativity with quantum mechanics. Now, I have rather two questions for you. The first is that we understand that still we are in the search of a kind of a theory which will unite the gravity, which is in a macroscopic or large scale, with the very small quantum mechanics. Now, my first question is that, is it that the mathematics or the experiment, as you rightly told that there is no deviation in experiments as far as quantum mechanics is concerned, is it that the mathematics or the experiment, I mean to say physical experiments, coincided and matched well with special relativity and quantum mechanics? Is that the reason that we find that special relativity and quantum mechanics and then the Dirac equation matched? Or is it because we know that there are some kind of infinities, rightly you told, that if we include gravity with QM, it will never happen? I mean to say, I want to understand what was the underpinning reason that special relativity, in spite of others, was an attempt to unite with QM.
Okay. I mean, essentially, we are looking at basically what is Dirac's story that way. Okay. So the first attempts, I mean, see, special relativity was fairly successful, and it also had a lot of theoretical background. Okay. Many people don't realize this, but special relativity was already there at the level of Maxwell's equations. Even before all these Lorentz transformations and all came out, people started realizing that Maxwell's equations are actually consistent with special relativity. They were always, okay? So, and Maxwell's equations predicted reality to an extremely high degree of accuracy. So Einstein did not want to let go of Maxwell's theory, okay? So in that sense, he said that, all right, classical mechanics has to go, or modified, I would say. And then, of course, special relativity was born from the postulates of special relativity, like the speed of light is invariant, or it's the same for all observers, irrespective of the state of motion. Okay? And that single postulate was so powerful that you have all the results of special relativity coming up. Okay? But then, parallelly, what was happening is, of course, Schrödinger and the rest, Max Born and all of those, Heisenberg, they were developing quantum mechanics to explain something else. Okay, something which was again very pressing at that time, like black body radiations and all of that, and it was not matching with our theoretical understanding. So then what happened is that naturally the question arose is that, okay, in its domain of validity, quantum mechanics explains things very well at atomic scale, and special relativity also happens to be what you call a true story of our universe. So that also has to be respected. So what happens if you try to unify? This is one of the, like you mentioned, Dirac equation. And fairly speaking, to my knowledge, when I read about the history of development of quantum field theory or Dirac equation, the story goes that Dirac was actually staring at, I don't know whether it's authentic or not, but this is what is mentioned in many textbooks. So apparently Dirac was staring at fire, and then he was like, suddenly got this idea that he came out with Dirac equation. But the original motivation behind Dirac coming up with this equation is the following. If you look at the non-relativistic quantum mechanical Schrödinger equation, it is linear. It's a linear equation. It's linear in the derivative of time. That means it is first order in time derivative. Okay, Dirac liked that, and he wanted to have an equation, similarly, a equation for a relativistic particle which respects that. It has to be first order in time derivative, just like in the case of Schrödinger equation. But the problem with that is that in order to do that, Dirac actually wanted to take something, how should I put it in a colloquial language? Okay, like since there are a lot of students here, so there is this famous equation in special relativity which says that a square of the energy is basically momentum squared times speed of light squared plus mass squared times speed of light to the power 4. Okay, there's this very standard equation. If you look at any special relativity textbooks, you have this equation. It's basically the energy momentum relation. Okay, so it's a generalization. It's a generalization of the classical Newtonian mechanics equation, which basically says that p square by 2m, where p is the momentum, m is the mass, p square by 2m is basically the energy for a free particle. In relativity, it gets modified to E square equal to P square C square plus M square C power 4. And it turns out that Schrödinger's equation you can get from that E equal to P square by 2M, non-relativistic equation, by just making some identifications. That if I take energy as associated with the time derivative operator, momentum associated with the spatial derivative operator, and then I introduce by hand something called a wave function, I get the Schrödinger's equation. In many textbooks, actually, it's written that Schrödinger's equation can be derived like that, which is not true. You cannot derive it. It's still a postulate. But Dirac took that hint and said that let me actually play around with this relativistic variant of it, and let's see if I can get an equation. The problem was that he actually got an equation. And now we know that equation, it goes by a name. It goes by the name of something called the Klein-Gordon equation. Okay, and when Dirac wrote it down, he interpreted the wave function as wave function for a single particle. But the problem with that is that it gave negative probabilities. If you compute the probability density for a single particle, if you interpret the wave function in that sense for a relativistic particle, it will give you negative probabilities. And Dirac was like, okay, this is not correct. And moreover, actually, he didn't like the fact that it had second order in derivative with respect to time. So in order to make it first order in derivative, you basically have to take a square root of p square c square plus m square c power 4. In order to take that square root, that actually was the motivation behind Dirac's equation. So it was purely theoretical. Okay, and taking the square root of that and replacing it by relevant operators, that gives rise to Dirac equation. But the radical difference is that when you do this and you apply it on a wave function, that wave function is no longer wave function of a single particle or a single electron. It has to be reinterpreted as a field. That's the crucial aspect. You do that, and then rest of the story actually falls in place. And Dirac was happy that it does not give you negative probabilities and all of that. And when Dirac came up with this equation, it was first order in time. In fact, it was also first order in all the spatial derivatives. But the object of interest was no longer a wave function. It was a much more complicated object. Okay, I believe I'm going to talk about this object much later in our conversation if the context comes up. Okay, but as far as Dirac goes, his motivation was purely mathematical and theoretical, and it turned out that it actually explained a lot of other things. It explained about the magnetic moment of the electron. It explained about the antiparticle came out naturally out of it, and it successfully unified quantum mechanics with special relativity without any pathologies. I should put it like that, without any pathologies. But it required a reinterpretation of the wave function. It is no longer a single particle. It does not describe the wave function for a single particle. It has to be reinterpreted as a field. Yeah.
Right. So what you're saying that, yeah, in order to remove the negative sign, you have to square and automatically equate. Okay, fine. Thank you, sir, for making a wonderful explanation. We have got a question. Stefan's law is a quantum mechanical effect or a classical, as it can be determined by statistical perspective, also quantum mechanics?
Okay, so that, all right, that's a good question. No, in fact, Stefan's law, you can derive it from pure classical, classical statistical mechanics. You can absolutely derive classical statistical mechanics. When I say classical statistical mechanics, by that I mean that you do not need to assume per se. Okay, so in the derivation, all you need to do is that you have to introduce basically some kind of a what you call resolution in the momentum and position. Okay, and that does not mandate that it has to be actually equal to the Planck's constant. It does not have to be. In fact, you can go about deriving the whole thing by just assuming that there is some kind of a resolution issue. That's it. In fact, the entire classical statistical mechanics, you can derive it from that. You just have to assume that there is some kind of a resolution that you need to put in by hand. But if you ask the question that can I derive Stefan's law from quantum mechanics? Yes, you can. Yes, you can. Of course, you can. In fact, you can derive all of the thermodynamics, all of this from quantum mechanics. Okay, because quantum mechanics, then you have what you call the postulates of statistical mechanics, which is basically the postulate that all microstates are equally probable. The moment you add that ingredient in addition to the postulates of quantum mechanics, you can of course derive Stefan's law. But it's not necessary that in order to get Stefan's law, you need to add in this extra ingredients of quantum mechanics. You can get all the results nevertheless. You can, yeah.
Thank you, sir. Dr. Professor Swagat Saurabh Mishra is already here. I would like to extend my thanks to him and gratitude. So he's telling that it is this: how to take a square root of an operator, which Dirac was thinking for a long time and got the new idea fireplace. Near fireplace.
Yeah, that's how the story goes. Yes, that's correct. Yeah.
Okay. Thank you, Swagat sir, and please stay on the podcast. Okay, we got a question. I don't know how it would be. I think, sir, this is relevant. Raghav Manchanda is asking, what is the multiverse according to string theory?
Okay, so we are jumping topics here actually from quantum mechanics to...
Yeah, I think, sir, you can answer and I will go sequentially from now on.
All right. Okay. So, so in string theory, what happens is that in order to consistently describe, string propagation in space-time, okay, there are mathematical constraints that you put in by hand. I mean, not by hand, sorry, my mistake, not by hand, but the mathematical consistency comes out of certain rules, all right? And once you plug in those rules, it turns out that strings have to propagate in a certain type of spacetimes. Okay, it has to satisfy certain geometrical constraints, geometrical as well as topological constraints. So technically, we now understand that they satisfy certain mathematical constraints that if people who know differential geometry or topology, it has to basically satisfy some mathematical condition like the Ricci has to be 0 and all of that. It has to be 6-dimensional, etc., etc. So I'm assuming that we are talking about what you call 10-dimensional string theory. Okay, I'm not going to talk about the 11-dimensional M theory because that itself is not understood well, and I am not an expert on that. But as far as string theory goes, which is the 10-dimensional string theory, for example, we have the type 2B string theory. In that, if you need consistent string propagation without any anomalies, then the space-time has to satisfy certain criteria. That means the 4-dimensional space-time that we can perceive, our senses can perceive, they of course can be what you call like they can be Minkowskian, that can be okay. But the 6-dimensional compact subspace, that has to satisfy certain criteria. And when we talk about multiverse, it turns out that you need to have additional conditions on string theory, and that it goes by a mechanism which is called the KKLT mechanism. It's a very famous and very complicated mechanism. On top of all of this, you add in that ingredient that basically means that I need to have not a Minkowskian 4-dimensional space, but I need to have a space which has a positive cosmological constant. Okay, that's called the KKLT mechanism. You impose this condition that I need my 4-dimensional large dimensions that I can perceive to have a positive cosmological constant and not Minkowski. That means it should not be flat. That condition basically puts an additional, what you call, it correlates with the additional subspace, which basically tells you that there are 10 to the power 500 compactifications possible of the subspace, the 6-dimensional subspace that is possible, which will give you consistent string propagation. Okay, so let me repeat this. I mean, this can get confusing slightly, so let me repeat and let me make sure that this is clear. So you have a 10-dimensional space-time. Okay, out of that 10-dimensional space-time, 4 of them, which is 3 space and 1 time, which are large, which our senses can perceive. And you ask the question that I need conditions such that the strings living in this space-time, they have consistent propagation, or they're basically consistent. The field theory of the string is consistent. The moment you put in these conditions, it turns out that, okay, as long as my 4-dimensional large space, okay, is Minkowski meaning flat and all of that, then the 6-dimensional subspace has to be compactified according to certain rules. That 6-dimensional compact space is called Calabi-Yau manifold. Okay, it's a geometrical and topological construction, and that is there, and it has been known to mathematicians for a long time, even before the advent of string theory. Now, but if you put in an additional condition that my 4-dimensional large space-time has to obey Einstein's equation with a positive cosmological constant, so that's an additional ingredient you're putting in, then it tells you that the 6-dimensional subspace that we are talking about, which are compactified, there are 10 to the power 500 possibilities. Okay, I mean, of the order. I mean, it's not
that
exactly.
Means you are saying, sir, that this 4-dimensional space that we see around, if you're plugging in that extra, all these problems starts happening. Okay.
Yes, yes. That basically means that you basically want a de Sitter kind of a space. So you want string propagation, consistent string propagation in de Sitter space. Then you're asking the question that, okay, what are the possibilities? Well, it is 10 to the power 500. And that is coming because the kind of compactifications or the kind of Calabi-Yau manifolds possible for this kind of a, what you call additional condition, it's 10 to the power 500, order 10 to the power 500. This is a very large number. So we don't know, like out of this 10 to the power 500, which is our universe, because each of those describe particles which are, which are very different. Okay, we don't know which one corresponds to our reality. So that's there. I mean, that's a problem. That's called the landscape problem, actually, in string theory. Yeah.
Thank you. That is, we got a very clear idea. Just one quick question: this Calabi-Yau manifold, etc., whatever we are talking, sir. I mean to say, are these visualizations on a mathematical front? Shall we call it like that?
Well, math says that they exist in reality. Okay. But they're so small. They're so small. They're like the compactification is so small that our we don't have experimental apparatus to like parse it or resolve it. Yeah.
So we have a question from Raj Roy, which is very relevant. We won't jump the topics right now. Sir, you have told that Schrödinger is a postulate, but it can be derived from equal to nc square and de Broglie equation.
Not true. That is not true. Yeah. The reason is it's not true is because of the fact that anything that is classical, for example, if you say equal to mc square or equal to p square by 2m and all of that, in order to get to Schrödinger's equation, you actually have to write down a few postulates. You first of all you have to say that there is something called the Hilbert space. That itself is a leap of faith. You are basically saying that there is something called the Hilbert space, and that does not necessarily exist in the real world. Okay, I'm constructing a mathematical framework. There is something called the Hilbert space. In this Hilbert space, there are states, or there are, since Hilbert space is also a vector space, there are vectors associated with this Hilbert space, which are the elements of this Hilbert space. Okay, and these vectors are basically what you say are the wave functions. And then you say that, okay, there is this wave function. What do I do with this wave function? Then you have to also, on top of this Hilbert space, you have to introduce other players, which are like operators. Okay, then what do you observe in the lab? You observe energy, you observe momentum. Okay, and how do I bridge this? You will say that associated with energy, associated with momentum, associated with any observable, like even angular momentum, I will postulate the existence of an operator. This operator will act on elements of the Hilbert space and give you back elements of the Hilbert space. So there is a lot of leap of faith going on. Okay. And lastly, you will say that there is something called the Schrödinger's equation, where there is something called the Hamiltonian operator, acts on an element of the Hilbert space, and it gives you the time derivative of the Hilbert space. Time derivative of that vector. Okay. And the Hamiltonian, it's an abstract operator. Only in the case of non-relativistic mechanics, it turns out that it works for p square by 2m or like whatever. Okay. In general, it does not work. Meaning, you can come up with a Hamiltonian classically for a particle in some kind of a weird situation, and it may not correspond to. You cannot just make replacements and you expect that it will also work in quantum mechanics. In fact, the best example is Dirac's equation. If you just take e square equal to p square c square plus m square c power 4 and you replace everything, you are not going to get Dirac equation. The non-trivial aspect is that you have to take a square root and all of that, and you have to again come up with something which you have to go away from the Hilbert space. Okay, then you have to look at something else. All right, and which I don't know whether I should speak about it right now because maybe I'm jumping the gun. But Dirac's equation is not for a wave function. It's basically for an object which is actually which we call a spinor, all right, which describes spin half particles. So it also describes spin naturally. Yeah. So it's not it's a myth that Schrödinger equation can be derived. It's actually a postulate. Yeah. It turns out. So let me again reiterate, because there are a lot of students here. I want to clarify this. So when you write down the Schrödinger equation, it basically says that there is a Hamiltonian operator. I'm talking about non-relativistic. Okay? Hamiltonian operator acts on the wave function, gives you the time derivative of the wave function, of course, with a factor of I and Planck's constant thrown in. Okay, that factor of I is crucial. Otherwise, you don't have Schrödinger's equation. You have diffusion equation, classical diffusion equation. So the factor of I is very crucial, and Planck's constant also enters there. But then, what do you do with this equation? I have to cook up an operator, which is the Hamiltonian operator. So what am I dealing with? Suppose I'm saying that let me deal with a free particle. All right, let me deal with a free particle. Classically, the energy is given by p square by 2m. I have to come up with a Hamiltonian. Okay, the Hamiltonian is also p square by 2m for a classical particle. Let me just try a replacement. And see whether it actually predicts reality. So what I will do naively is that I will take p square by 2m. I will upgrade the status of p to an operator operating in Hilbert space, and I will replace p by a differential operator. Okay, if you are working in a certain basis, I will just write p as some spatial derivative with some I and h cross thrown in, and I'll plug in to the what you call so-called Schrödinger's equation, and I will check whether it actually predicts reality or not. If it does, then that's a correct what you call trial that you came up with. But otherwise, it's not true. It's not necessarily true. In complex situations, you cannot just take a classical Hamiltonian and just translate it to something called quantum mechanics. It doesn't work.
Right. So we have got a few questions coming up, but before we move ahead, I need to set the stage for going to the next part. My question, sir, to you is that when we talk of this, the concept of Dirac equation, that it predicted antimatter before it was experimentally discovered, what does this tell us about the relationship between mathematics and physical reality? That Dirac equation predicted antimatter before it was experimentally discovered. So does it say something regarding mathematics and the physical reality?
Okay, that's a pretty deep question, and so this again is heavily debated. And let me quote. There's this MIT physicist by name Max Tegmark. And in his book, he claims actually that whatever is realized in mathematics consistently will have a physical manifestation in nature. That means he claims, and I think there are a set of physicists which believe this, that whatever is realized mathematically will have a physical manifestation. I mean, it will be used as a framework to describe real physics at some point of time. I personally am not too much what you call convinced by that argument, but the converse definitely happens to be true, that whatever happens physically needs to have a consistent mathematical framework. I mean, it requires a complete consistent mathematical framework. There's also what you call a saying that math is at least 100 years ahead of physics. That basically means that the math that you're doing now seems very abstract, and 100 years later physics is going to use it. All right, and that also ties with what the kind of remarks that Max Tegmark makes, that whatever we are doing today in mathematics will eventually be used in physics, and it has to be. That's a stronger constraint. Okay, that's a stronger statement or a stronger claim that he makes, that whatever, for example, I'm doing some abstract but consistent, okay, some abstract mathematical construction. I don't know. I mean, 100 years down the line, maybe there is some kind of a fundamental theory which is going to use that as a framework. But what I know for sure, and I think as a physicist, that is what I am legitimately allowed to speak, is that whatever physical reality we see today does in fact come from a very, very consistent mathematical framework. And it is also true that whatever mathematical framework is being used, it was always ahead of physics at that time. For example, Riemannian geometry was like
much ahead to general relativity.
Okay.
Yeah. The concept of manifold, etc., all emerged almost 100 years earlier, which was later used by Einstein much later.
Yes, and by that same logic, the concept of what you call, if I may say, I mean, the whole concept of what you call exterior algebra and all of that, from where basically now we connect it with what you call spinors and all of that, Dirac cohomology and all of that. That we knew it. I mean, mathematicians knew it much earlier. So that's what I would like to say, that whatever physics we know today, we owe it to the framework developed by the mathematicians much earlier. But whether whatever is happening today in mathematics, in the field of mathematics, whatever abstraction we come across, or whatever consistent construction we make today, whether that will become a framework for the future fundamental theories of physics, that we don't know. That only time will tell. Yeah.
We have got many questions coming up. I have to take one by one quickly. First question is coming up is, just a second. Yeah. Abhijit Kumar is asking, sir, can we say the holes which form in topological string is a function of some scalar field?
I'm not quite sure I follow this question. I mean, can this be rephrased slightly? I mean, what scalar field? Like, is it the dilaton or something like that?
Yeah, I would request Abhijit if you can rewrite this question, and then we will come and take it apart. Astrotech is asking, why do quantum fields have infinitely many degrees of freedom, but experiments always involve a finite number of particles?
Oh, I see. All right. Well, I think there are two portions to this question. One is that quantum fields have infinite degrees of freedom. What do you mean by infinite degrees of freedom? Let me just first answer that. Okay. So in quantum field theory, in fact, that is one of the reasons why you need quantum field theory, is that the particle number is not conserved. What do I mean by that? All I mean by that is that I can create and destroy particles. Okay? And where does that come from? Well, that comes from relativity. Actually, that you should appeal to relativity. So let me give you a very quick, heuristic argument for that. So in relativity, energy and mass, they're equivalent, of course, equal to mc square, and c is set to 1 because it's a universal constant. We always need not set c. Okay, I mean, put c in our equations. We set it equal to 1 forever. Then, so energy and mass are equivalent. Once you accept this reality, if you focus, or you what you call localize sufficient energy in a what you call you localize sufficient energy in in a portion of space, it basically tells you that you can create particles in order to accommodate. And we also see that in our accelerators. That means the particle number is never conserved. Two particles can go to three particles, and all of that keeps happening. So how do you account for that? In order to do that, you need quantum fields, and quantum fields need that infinite degrees of freedom in order to accommodate this kind of a structure. All right. The second part of it is that, but we see finite number of particles in experiments. Well, that actually is a slightly different question. Okay, because our experiments we have not yet probed till the Planck length or the Planck energy. All right, we have not probed till then. So our experiments are limited in that sense, in terms of how much energy we are able to smash them and to study the substructure or the subatomic structure. In fact, if you believe in string theory, I mean, again, I'm using the word believe, like, okay, if string theory is right, then there are infinite particles actually, and you will have more and more particles as you keep pushing the energy scale. So yes, so as far as quantum field theory goes, you need the infinite degrees of freedom inbuilt into the quantum field so that you can accommodate this what you call feature, that particle number should not be conserved. It better not be conserved, otherwise it will be inconsistent with relativity. Point number one. Point number two, we do not yet know whether the number of fundamental particles in our universe has a limit. We don't know that. String theory says there is no limit.
Okay, thank you very much. Just a quick note to all those who are watching this. On the 27th of September, 2026, I am conducting a webinar, which I've conducted successfully on 15th of August. Just a quick note, those who want to participate in this webinar with a nominal fee of 200 rupees, there I have got my WhatsApp number and my email ID over here. Please drop me after this podcast. Those who want to join, I will send you a Google form. You can fill it up, do the formalities, and book your seat. This time I am teaching general relativity overall with a special emphasis on the concept of tensors and how tensors are used in general relativity, and what are the Einstein field equation, the Ricci tensor, etc., how they are built up. And so overall, you will learn general relativity with a special emphasis on tensor. You can contact me later. You have my WhatsApp number 98302196777, and drop me an email and book your seat, because I won't be taking a huge in number. We have to interact and make the webinar much more fruitful, concentrating on tensors. That's it. Okay, sir, I actually had a question, but there are so many questions coming up, which is a little bit, if you can answer it in short, because there are so many questions coming up. Now, what we see is that the spin concept of spin actually automatically comes, or it emerges from the Dirac equation, even though it has no, I would say, classical similarity or classical analog. So if you can tell us, what does spin really tells us about the quantum reality? And it's something which is, when we learn, we know that it is not a spinning top. That is a wrong analogy, but it is an internal. So if you can let us know, you're the best person to tell.
Okay, and I'll tell you an anecdote. The anecdote is that when I came across spin for the first time, I felt that actually the roots of spin lie in quantum mechanics. But it turns out it is not true. The roots of spin actually lies in relativity. Okay, let me quickly explain how. So when Dirac came up with his equation, so he took the square root of that p square plus m square, okay, and that led to the Dirac equation. Yeah, you can do that. In fact, many textbooks actually do that. Okay, but there is also the modern way of looking at Dirac equation. Okay, and it comes from group theory. So the way you look at the modern way of looking at, in fact, any field equation, even if it's Klein-Gordon equation, Dirac equation, any equation like that, the fundamental starting step now is group theory. So what we'll ask, so we ask a question, is that, all right, we have a space-time, which is basically called Minkowski space, and there's a metric associated with it. And then you ask the question, what are the symmetries of this? Okay, what are the symmetries of the space-time? It turns out that there's a group called the Poincare group. And in a nutshell, Poincare group is basically that my space and time is invariant under spatial rotations. It's also invariant under Lorentz boosts. Okay, and it's also invariant under translations in time as well as space. So all of this combined, it's called the Poincare group. Then in group theory, the standard practice is that you ask what are the representations of this group. Okay, this is, by the way, let me tell you, when you go about this in practice for graduate students who are attending this seminar, or undergrads who want to do this, if you come across angular momentum in quantum mechanics, okay. So what you do is that you have three components of angular momentum, and then you take like something called a Casimir operator of the angular momentum, which is basically the jx square plus jy square plus jz square. And it turns out that this is very special. It commutes with all other angular momentum operator. It commutes with jx, jy, jz. So in quantum mechanics, there is this concept that you can simultaneously diagonalize two operators. Okay, and if you can do that, then you can form a basis. All right, it forms a basis. And this is standard, what you call completely standard exercise in quantum mechanics. It turns out that in group theory, this is what you do. Mathematically, it's exactly that. So you take the group, which is called the Poincare group, and you ask what is the representations of that. In order to do that, you actually find out exactly in the same way that you do it for angular momentum in quantum mechanics, you do it for the Poincare group. But this does not have anything quantum. Absolutely nothing. But the math actually is very, 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 very similar. You do that, and it turns out that there are representations of this Poincare group. The most trivial representation of this Poincare group is something which describes, which we call as the spin. Okay, which it's a name. It's basically a kind of a particle, which is completely, I mean, not a particle. It's an object. I would rather put it like that. It's an object. Okay. The lowest representations of the Poincare group, if I may put it, it's an object which does not transform under rotation, Lorentz boost, translation, nothing. In modern physics, that representation is identified with the scalar field.
So, sir, if I'm taking it right, then you're telling that Poincare group already had an object which represents the concept of spin.
Yes. So the next what you call representation, which we call, so this is called the spin zero representation, which is called the scalar. Okay. Then you ask there is also the spin half. Spin half, okay. The spin half representations of the Poincare group, you are forced by mathematics to encounter an object which under rotation or Lorentz boost behaves in a very, very counterintuitive way. Okay, and it basically tells you that if you apply a normal rotation to this object, it does not come back to its original configuration. You actually need 2 times, so 720 degrees, and you'll back to the original configuration. Okay, so this kind of construction, and it has nothing to do with quantum mechanics. Okay, it is purely a representation of the Poincare group. It's called the spin half representation of the Poincare group, which actually forces you to encounter something called the spinor. And to complete the story, you will ask the next level. Okay, spin zero, scalar field, spin half, spinor, spin one. What do I get with spin one? Well, you get vector fields. You'll get vector fields. And from vector fields, of course, then the next question is, what do I do with these things? I have a scalar field which behaves under rotations or Lorentz boost in a particular manner. I have a spinor field which under rotation, Lorentz boost acts in this way. I have a vector field, and so on and so forth. What do you do with this? So the next step is that, all right, I have these objects. I need to have some kind of a Hamiltonian or a Lagrangian so that I can do physics with it. And when you do that, you have a lot of constraints. It has to be consistent with the Poincare group. That means you cannot arbitrarily add or subtract or do these things. And in order to accommodate time, what you call dynamics, these fields better accommodate derivatives with respect to space, derivatives with respect to time. But these derivatives has to also combine in a special way, so that Lorentz group, or the Poincare group, the symmetry of the Poincare group is always respected. So in fact, if you put in all these conditions for a scalar field, you will be led to Klein-Gordon equation. If you put these conditions for a spinor, that means the spin half field, you will be led to the Dirac equation. If you put these conditions on a vector field, spin 1, you will be led to electrodynamics. That's it. So it comes from group theory.
Right. So the spin actually existed in the Poincaré group, and we
Yes.
actually did not notice something like that.
Yeah, I mean, Dirac didn't know this. I can tell you for sure that Dirac did not know this, that it already comes from group theory. Okay. For him, it was more like an algebraic exercise. All right. But the moment you look at it from a group theory perspective, all these seem unified. So it's more like a unification, like symmetries are the starting point. This Klein-Gordon equation, Dirac equation, or in fact the Maxwell's equation, they look very different. They do not seem connected with each other at all, but they are all connected at the level of the Poincaré group, which is basically the symmetry of our universe, of our space-time.
Right, right. And
Yeah.
as far as I know, sir, history tells that Poincaré group and this actually came much earlier to Lorentz transformation, but somehow we don't actually work much on Poincaré group, but we talk about Lorentz transformation and the gamma factor. But history
Yes.
tells that it come much earlier to what
Yes.
Einstein actually did. Right.
Yes,
Okay.
absolutely. Absolutely.
Okay.
Absolutely. Yeah.
So we have two questions coming up. I will take one by one. Rayleigh is asking, sir, how much progress has been made for the grand unified theory?
I mean, there are so many variants of grand unified theories, like depending upon, again, starting with groups like SO32 and all of that. I mean, when I say SO32 or something like that, it's basically, it assumes certain group structure. I mean, symmetry structure of our universe and of the particles, and it starts from there. Okay, then there is supergravity theories. So under grand unified theories, it's basically a family of many physics theories which claim to be grand unified theories. In fact, at a certain level, you can also say string theory is also a part of can it be called as a grand unified theory? In my opinion, actually, they have all hit some kind of a roadblock. Okay, and progress has been stalled for quite some time now, and we are still seeking some kind of a breakthrough in all of those. And one of the breakthroughs that could have helped us is if we could have seen some kind of verification or experimental hint of something like a supersymmetric particle or something like that. But unfortunately, we have not seen that yet experimentally. So, and theoretical progress has been quite limited on that front after the initial rapid progress, but now it has kind of like slowed down. So, yeah, and that's true. But that's how.
Actually,
That's how.
this is a very,
Yeah.
it's a very open-ended question. What progress
Yeah.
has been made? Because there are a lot of things which are still going
Yeah.
on.
So for example, if you ask a hardcore string theorist and who's like a devout string theorist, he will say that a lot of progress has been made, and the best thing that has happened is that yes, gravity comes out of quantum theory. Okay, so you have strings on non-trivial backgrounds, and you apply the rules of quantum mechanics to it, and pop comes out Einstein's field equation. And this has never happened before, so this already is fantastic progress. It's unification of fields. Okay, but depending upon who you ask, if you ask someone like a Carlo Rovelli, he will say that no, there are 10,000 problems with string theory, and it's not the theory of everything that we all hope to be. Okay, so it depends on whom you ask, but credit has to be given where credit is due, and I believe that yes, a lot of progress has been made, but it has also stalled in the recent years. So that's where the assessment lies.
So one just small quick question. Now,
Yes.
Professor Leonard Susskind is considered to be the father of string theory. Is
Yeah.
it because we all know that he is a great teacher? We have been, observing his lectures at Stanford University. Even he is famously known for this holographic principle, solving the information paradox. In terms
Yes.
of string theory, why is he known as the father of string theory? Is it a kind of an invention, any mathematical theorem? What is his exact contribution? If you can throw some light on that.
Well, so it turns out that a long time back, like in the late 60s, there was a lot of data coming out. Okay, and scientists were actually finding it very difficult to explain the plethora of particles that we were observing and to catalog them in any kind of a consistent manner. All right. And it was like a zoo. It was completely like a zoo. Like particles were like popping in and out, and then we have no idea where, like, how do you catalog or how do you make sense of that? So then it turned out that Leonard Susskind, he made, I mean, again, it's purely stories, and we don't know exactly what led him to do that. It turns out that he just made an assumption that let's assume that we have a string. Okay, we have a string, and I will apply the rules of quantum mechanics to the string. And the moment I do that, it turns out that I can explain the particle data, okay, that was coming out at that time. It appeared so at that time. But later, it turned out that no, there is still some kind of a deviation from what Leonard Susskind's theory is saying, and we have a better theory, and which we came to know as quantum chromodynamics. Okay, and that explains the data far better, and there is a very good experimental match. So when that happened, obviously Susskind's hypothesis or Susskind's proposal, I would say, fell apart, and it was like put like in the side. It again, I think, in the early 1980s, I think Michael Green and Matthew Schwartz, these guys again picked up Susskind's proposal of considering strings as representing particles and not as point particles but as strings. Okay, and they actually figured out that forget about explaining the particle data of the 60s, late 60s, but this property that you do not have point particles, but you only have strings as fundamental entities of our universe. And when you apply rules of quantum mechanics to it, or quantum rules to it, it turns out that not just gravity comes out of it naturally, but it also cancels a lot of anomalies, mathematical anomalies that were plaguing the attempts to unify quantum field theory with gravity at that time. Okay, so it solved a lot of problems. Naturally, it solved a lot of problems at that time. So it was reborn, and it was what you call reinterpreted as not a theory to explain nuclear data at that time, but as a framework to explain unified field theory of all fields, including gravity. So yeah, that's the reason why Susskind is considered to be the father of string theory, because he actually started it all with that calculation. And of course, much later, again, he became what you call interested in application of string theory to information loss and the rules of complementarity, complexity, and all. He's very active in that field right now. Yeah.
Sir, a few questions coming up quickly. First is that Saxena is asking, now that you have mentioned about landscapes, can you explain what is the Swampland conjecture?
Okay. To be fair, actually, I don't work on landscape. Okay, and I would like to give you a very precise, what you call precise answer to that, but I would. Okay, can we come back to this later? I mean, I will still formulate a proper, what you call, colloquial answer.
Sure. Not a problem.
Because to my knowledge, actually, the moment you actually end up in a landscape and the probes of those landscape in strings, that's fairly confusing. Okay, and then you have to go to anthropic principle and all of that. So yeah, maybe later we'll come across it in a right context.
Not a problem.
Yeah.
Okay, we have a question from Muzammil Akhtar. Professor, you have mentioned the spinor. Please explain the difference between Weyl's and Dirac spinor and the connection of chiral symmetry breaking in quantum chromodynamics.
Okay, so basically, all right, I'll give you the answer. Since there are a lot of other students also, I'll give you a fairly, what you call, semi-technical answer. So there are various forms of the spinor which actually come from the Lorentz group, all right? I mean, Poincare group. and which one to use. All right, which one should I use, a Weyl spinor or a Dirac spinor? And the answer to that lies in the fact that it does not matter as long as the Clifford algebra is satisfied. Okay, as long as the Clifford, it's consistent with the Clifford algebra. Now, Clifford algebra is it's an algebra that the spinners have to obey. Okay, and any representation of the Clifford algebra is fair game. Now, which one to choose again depends on the context. If I want to explain something like a chiral symmetry breaking or something like that, then I will use the Weyl spinor. All right. If not, otherwise, if I'm just explaining what is the magnetic moment of an electron in a magnetic field or some electromagnetic field, I'll use a Dirac spinor. So it depends whether I'm trying to explain neutrinos. Okay. So which representation of the Clifford algebra I need to use? All of them obey the Dirac equation, of course. Okay. And they consistently, you can also couple it with the kind of field you are interested in answering the question. That's also a determinant of which representation of the Clifford algebra you need to use. So that's about it. So does that answer your question by and large?
Yeah, I think so. Let me wait for the comment. I think sir, yeah, that was a wonderful and a very precise answer to what you told.
So yeah, again, we are looking at representations. Yes.
Yeah, yeah. Okay, Abhijit Kumar, follow-up question. Sorry, Astrotech is asking. If we start just from the Poincaré group and its representation, why do only certain spins and particle types show up in nature and not others?
Well, yeah, that. Let me give you a counter example to that. Okay, so it turns out that in 3 plus 1, that means 3 space and 1 time dimension, what you are saying exactly happens. That means either you have integer integer representations or half integer representations. Okay, that's the reason why you have spin 0 representation, spin half, spin 1, spin 3 by 2, and all of that. Okay, but suppose you relax the condition that, okay, let me consider 2 space and 1 time dimension. So you are in some hypothetical world which is like 3-dimensional. All right, it turns out that you can have fractional representations also. That means it does not have to be half integer, and they go by the name anyons. Okay, so yes, it is possible, but it just turns out that in our 3 plus 1 dimensional space, that's the only possibility you have. But you relax that and you can have many other possibilities, especially in the lower dimensions. You have anyons. Yeah. And in fact, let me also add to this that I know about this because my advisor's advisor, Frank Wilczek, he worked a lot on anyons and he gave a lot of talk when he was visiting Arizona State University. So he was looking at the representations of the Poincaré group in 2 plus 1 dimensions, and there he actually showed that you can have fractional spin representations as well. Yeah.
Raghav Manchanda is asking a question. Just a second. What is liquid electron behavior?
No, I'm not.
I am
I'm not
also,
sure.
I am also a little bit clueless about this question. Okay, I will move to the next part of our podcast. Now, when we covered the quantum mechanics and the relativistic part, we understood Dirac equation, the prediction of antimatter, and we learned a lot from you that why by squaring and moving out the negative effect, the Dirac equation antimatter came through. Now, when we talk, sir, of quantum field theory, we get a popular notion that even the vacuum is a quantum state with structure, particles pop up and they vanish, they create and annihilate. So what does actually empty space here means?
Okay. So there's an underlying assumption. Okay, at the level of quantum field theory, that is, there are always quantum fields pervading space and time. Okay, without quantum fields, there is nothing. I mean, there is. If you say empty space at the level of quantum field theory, it basically means vacuum state. That means there is no energy and no particles. That basically means that the vacuum state or the field is in its lowest excitation configuration. Let me put it that way. The quantum field is there. Nevertheless, it's there. That's in fact that is the starting point. Okay, that there is a quantum field. But if it's empty space, by that it means at the level of quantum field theory, it means even though there is a quantum field, there are no excitations. Okay, there are no excitations, so there is no particles, there is no energy associated with this excitation. But definitely the quantum field exists. Yeah.
That is what empty space means.
Yes.
Okay, okay, okay.
I mean,
This is a, yeah.
one can go about from a philosophical perspective that where did the quantum field came from? I mean, that we don't have an answer to. Nobody has an answer to that. Yeah.
So when we talk of that Hawking radiation, sir, particles,
Yeah.
one particle falls inside the black holes, another particle escapes. So that is
Hmm.
also basically taking place considering the mathematics of quantum field theory, which is happening on the event horizon of black hole. Is that so?
Can you come again?
I'm
Actually?
saying that when we talk of Hawking radiation, when the particle,
Mhm.
one particle is throwing inside an event horizon, another escaping, and that black hole entropy, what we are talking. So we are, in that case, we are also considering the concept of quantum field theory applied to the horizon of the black hole. Is it so?
Yes, that's exactly right. I mean, that's what you do. So you consider quantum field and the vicinity of the event horizon. Okay, there is all sorts of what you call quantum fluctuations going on, and in fact, there is this very famous paper by my advisor Maulik Parikh. Okay, so the way he Hawking radiation can be visualized is basically there are these quantum fluctuations very close to the horizon, particle antiparticle pairs being instantaneously created, and of course they recombine and they disappear. But it so happens that there is some probability. Okay, there's always a probability associated that if it's very close to the horizon, then what happens is that the antimatter, okay, the antiparticle can actually fall inside the horizon and will be sucked in into the black hole, and the particle can actually escape to infinity. And that's that particle that escapes to infinity. That's what we see as a Hawking radiation. All right, and the antiparticle that fell inside the black hole that effectively works as reduction of the mass. So yeah, so it's quantum field theory in the background of a black hole or in the background of an event horizon that leads to Hawking radiation. That's
So,
also Hawking's original calculation.
yeah, in a very crude way, the way I am sitting, you are sitting, in front of us also, we have the field fluctuations going on all the time, isn't it?
Yes,
And the same
yes,
fluctuation is happening on the event horizon, nothing special as such.
yes.
But only because of the curvature, etc., something goes in and the opposite part escapes to infinity.
Actually, I would like to take this opportunity to clarify something. Okay, and so I don't work a lot on general relativity. I mean, I, I use general relativity, but I'm not concerned about the deep foundations of general relativity as such. Okay, but there is one misconception that I have observed is that people believe that event horizon, that location of the event horizon, is going to always have some kind of a tangible physiological impact on someone who crosses that. Okay, that is not necessarily true. In fact, the proof is pretty simple. Event horizon is special from a like if you look at it from a space-time perspective, it is actually special. Yes, in that sense. But if I ask a question that if I fall inside the black hole, I cross the event horizon, will I feel something funny? Not necessarily. Not necessarily. The reason behind that is that consider a very big black hole, like you're looking at 10 to the power 6 solar masses or something like that, massive black hole. Then what happens is that the event horizon for such a black hole would be at a location far away from the singularity. Okay, far away from the singularity. In fact, the Schwarzschild radius would be huge for that. And if you compute the tidal forces of the, even simpler, compute the Riemann tensor or the Riemann tensor squared. Okay, at that location, it would be, I mean, the tidal forces would be like fairly manageable. I mean, very normal. So any person falling inside the black hole of such a black hole, crossing the event horizon, would feel nothing, absolutely nothing. That person would start feeling something as he or she closes into the singularity. Okay, so that's something I want to clarify. That uh, event horizon in that sense is it's special. That yes, it is there, but it's also kind of unremarkable from a different perspective. Yeah.
So, in one sense, that smaller the size of the black hole, then only we can feel the effect, possibly. Something weird is going on.
Yes, that's because you're also closer to the singularity, space-time singularity. I mean, so-called singularity. We don't know what is happening there. I mean, that's still an unanswered question. Okay. I think there's a problem with the audio. Am I audible?
Yeah. Sorry,
Okay,
I
yeah.
was in. Yeah. As we transition from standard quantum mechanics to quantum field theory, how does our understanding of the quantum Hall effect change, and how do
Hmm.
effective field theories like Kern-Simon's theory?
Okay. Uh, well, I don't think there is a quantum mechanical analog of the Chern-Simons theory. I mean, it's a it's I don't, yeah, to my knowledge, actually, it's always a field theory. I mean, it's always a field theory. Even at the classical level, it's a field theory. And the moment you apply quantum rules to it, yeah, it's a quantum field theory. And as far as quantum Hall effect goes, well, the only thing is that the moment you understand quantum Hall effect from a field theoretic perspective, it's uh, it's more like a reinterpretation. And even though the final answer actually, the final answer is almost very eerily similar to what you will get from quantum mechanical perspective, but it all depends on like the consistency. Okay, the quantum field theory is a much more consistent description of how you get there. I'll give you an example. I'll give you an example from a very different perspective. If you look at the Schwarzschild metric, okay, I'm digressing here, but if you look at the Schwarzschild metric and you see that where is the what you call location of the event horizon, a simple calculation will tell you that it is at 2 gm by c square. Yeah, 2 gm by c square, something like that, right? This also eerily matches with the Newtonian calculation that if light has to escape gravity, okay, then what is the escape velocity it needs to have? If it has to escape from a star of mass m and radius r and all that, it will actually get exactly the same answer. But that does not mean that the Newtonian calculation is correct or complete. Okay, the right way to look at it is from Einstein's general relativity and the reinterpretation via the Schwarzschild metric. Similarly, the quantum Hall effect, the right derivation of it is through quantum fields and then the application of what you call the external electromagnetic field, and then computing the charge density and the flux. All right, that calculation through field theory is much more complete. Even though the final answer, yeah, it looks as if like, yeah, I could have as well done it from quantum mechanics, but it's not true. Many things are just put in by hand when you do it through quantum mechanics.
Okay. Thank you, sir. Thank you very much for a very lucid and clear explanation. Astrotech is asking if quantum fields are fundamental and particles are only excitations of those fields, then what
Mm.
actually exists when nobody is measuring anything?
Okay. All right. So basically, we are bordering on some kind of a philosophical and ontological questions as far as physics goes. So imagine a universe where there is quantum field, and there was I think this question is probably stemming from the fact that only when I measure is there an excitation of the field. That's not necessarily true. You can have a quantum fluctuation with a sufficiently high amplitude, okay, such that the energy associated with that amplitude actually corresponds to creation of a particle. And if the particle comes into existence, it will stay forever, irrespective of whether I observe it or not. That is always true. So that all depends on what the initial conditions were and what was happening. So, for example, I'll give you a much more heuristic answer. In the beginning of the what you call the beginning of the universe, there was no observer. Nobody was there to measure the particle, but we still see particles today. Where did they come from? It is not that we created them, or there was somebody who observed them, and then the quantum fluctuation came into being. Quantum fluctuations are what you call property of the nature, and it's the reason why we have the kind of particles that we see today, and the spectrum of particles, all right, or the spectrum of the fundamental particles. The reason why we see them today the way they are is because of all the quantum fluctuations that happened in the beginning of the universe. And why did it happen like that, and what created that, and all of that, that's still an unanswered question. We don't know that. The assumption is that quantum fluctuations were there. Yeah.
questions coming up. This is a little bit different. I think you would love answering it, sir. AI is solving many mathematics questions which were unsolved from decades. So my question is, will AI in future replace mathematician or theoretical physicist? My dream is to become a mathematician.
Okay. All right. Personally, I'm very scared for that future. I don't want to be obsolete. All right. But that's a very difficult question to answer right now, to be honest. I personally don't know. Okay. And I have been following some developments where AI has proved certain theorems or actually has hypothesized certain conjectures in mathematics. Whether in future it can solve quantum gravity problem, can it unify gravity with quantum field theory or quantum mechanics or something like that, that's something we don't know. I don't think anybody knows. I think if you ask this question to even Edward Witten or say Ashok Sen, they would also say we don't know the answer to that right now. Yeah, but maybe somewhere down inside, I believe maybe we cannot rule that out also.
That is true. That is true. Okay. So Preetham Roy is asking, in Hawking radiation, why only antiparticles fall into the black hole and particle escapes the event horizon? Why not particles fall into black hole and antiparticles escapes the event horizon?
Ah, that's a fantastic question, actually. All right. Uh, okay, I'll tell you the answer to that. Okay, this picture, that particle antiparticle pair that I gave you, this is also very intimately related with the fact that if you look at the Schwarzschild metric, the moment you go below, I mean, below the event horizon, space and time actually flip. Okay, space acts like time and time acts like space. All right. I'm again talking very heuristically. There is a rigorous way to put this. All right. But I'm talking heuristically. And what I call as antiparticle is basically something like traveling back in time. Okay, again, heuristically. So what we say is that always the antiparticle falls in or the particle does not fall in. That is technically not correct. The right way to put it is that whatever falls in, it actually is the antiparticle as seen from an observer, as interpreted by an observer, which is like at infinity. That's the right way to look at it. Does that answer your question, Preetham?
I think that's so. I mean to say, what you're saying, sir, is the coining of the term is not correct. What is happening?
That's
Right.
not correct.
So what falls in that particles, some antipart escapes. That's it. I mean to say, it doesn't matter
Yes.
whether it is a particle.
Doesn't matter actually which one. One of them has to fall in, the other one escapes. All right.
Right.
Yeah.
So if I have got my anti, I will fall in, and the my part will escape. Right.
Yeah.
Okay.
Yeah. That is.
Mohit Takral is asking, QFT successfully blends quantum mechanics with special relativity but fails with gravity. What is the biggest conceptual roadblock when extending QFT to gravity, and how does string theory fix it?
Okay, so that's a good question, and the answer to this is many folds, many reasons, many roadblocks actually why it does not happen at the very, very fundamental level, absolutely fundamental level, is that pardon me, is that quantum field theory assumes that there is a quantum field and there is always violent fluctuations of the field. Okay, so at any instant of time, the quantum field is never innocuously silent. It's always fluctuating. It just turns out that the amplitude of those fluctuations are small in the sense protected by the uncertainty. You'll never see them. Okay. And for whatever reason, if the amplitude becomes large, suppose you localize energy spatially or something like that, then the amplitude jumps up and then you see a particle. Okay. That's the whole fundamental foundational principle of quantum mechanics. Now, what happens with gravity? Now, gravity, as per Einstein, it's actually the theory of space and time itself. So, in this sense, the field of interest is space and time itself. If you have to apply quantum rules to space and time, that basically you have to assume that space time itself is not innocuously what you call smooth, there are fluctuations in space and time itself. Okay, there's fluctuations in space and time itself. In other words, space time is not smooth. When I say smooth, somebody who knows differential geometry, if you have come across the concept of a smooth manifold, okay, you need the manifold to be smooth in order to define or in order to do calculus. I mean,
absolutely,
you need
absolutely.
smoothness to do calculus. Otherwise, you cannot do calculus.
Otherwise, we cannot do. So smooth manifold, and that enables us to do the calculus. With jumps and corners, we cannot do it. Right.
Absolutely. Okay. Absolutely. So this is the heart of the problem. You apply quantum rules to space-time directly. You need the space-time to be violent. Okay. And the moment space-time becomes violent, you lose the idea of a smooth manifold over which you can do calculus. This is the heart of the problem. Okay. Of course, there are multiple manifestations of this. The manifestations of this is that quantum field theory always assumes that the excitation of the quantum field is to be interpreted as a particle which is of a dimension 0. Mathematically, it has dimensions of 0. Okay. The moment you assume this as well, then there are other problems. The other problems is basically, like somebody asked me in the beginning, right? Ultraviolet cutoff and all of that basically means when particle comes very close to each other. Okay, when particle comes very close to each other, then you have infinite forces. Again, heuristically speaking, in order to tame those down, you need there are programs there are techniques in quantum field theory to deal with that. Okay, but the problem happens with gravity. One of the problems happening with gravity is that this is completely incompatible. When you try to model space-time as a field itself. Okay, when you model space-time as a field, excitations of the space-time as some kind of a field, and the interaction of this field with particles, you actually do not have the tools with quantum field theory to actually alleviate the problems. I would say that you still have a lot of issues in normal quantum field theory, but you can alleviate them using tools of quantum field theory. Okay, but the moment you apply that to space and time and fluctuations of space and time interacting with other particles, there are a lot of mathematical difficulties. You just do not know how to deal with that, and you'll get a lot of nonsensical answers, anomalies. Yeah. So QFT is not equipped. QFT is not equipped to to be extendable
to smooth manifolds.
To smooth, yeah, that's not possible actually. Yeah,
actually, wonderful. I mean to say, sir, we really appreciate, and I can very well understand that is why students love you so much. I mean to say, your answers are incredible. Okay, Cipher singularity.
Let me just tell you something. Okay, I mean there are many roadblocks. Okay, there are also another way to look at this whole thing is basically the coupling constant. Okay, in interacting field theories, we have something called the coupling constant, which basically tells you how the particles interact with each other. Okay, the strength of the coupling, which tells you how the particles interact with each other. And this answer is geared towards students who are slightly advanced. Okay, in general, in quantum field theory, the coupling constant are dimensionless. Okay, dimensionless, so that you can actually have a consistent effective field theoretic description of it. In gravity, it turns out that is not the case. It is not dimensionless, and the way the coupling constant appears in gravity for Einstein's field Einstein-Hilbert action is what I would say. That makes it extremely difficult to have a renormalizable quantum field theory. It's not possible. Yeah.
Okay. Thank you, sir. There's a question coming up from Cipher singularity. Professor, if from starting quantum field is present in our universe, then which thing is generating excitation on it?
Okay. So that's pretty random, actually. I mean, that's pretty random. I mean, why should an excitation happen at some point in space and time? That is completely statistically a random process. I mean, we have no rule which says that it has to happen in a certain way, or it has to follow a certain consistent pattern, I would say. Okay, like again, it connects with my earlier answer, is that the particle content that we see today in our universe, we know that it is due to quantum fluctuation, including the galaxies, all the particles that we see today. It is because of quantum fluctuations that happened much, much earlier, okay, when there was no observer, nothing. But what caused exactly that amount of excitation, or where it happened, okay, that is something completely statistically random. I mean, it happened everywhere. I mean, that's what we say, that it happened everywhere. But there are a lot of unanswered questions also. If it happened everywhere, then why don't we see parity in matter, antimatter, and all of that? Where did all the antimatter disappear and all of that? Those are still unanswered questions. We don't know that. Yeah, but it happened. Yeah.
Old Manish, IIT Kharagpur, telling that why theory. No, this is not the right question. Yeah. What do you think is quark-gluon plasma proves string theory going in right direction indirectly, as we cannot test string theory directly?
No, actually, okay, let me put it correct. Let me put it more precisely. Okay, so this quark-gluon plasma is coming from some kind of a phase transition that happens in quantum chromodynamics. It's a very different theory. Okay, it's a quantum field theory, a fairly successful one. In string theory, what happens is that we actually have an analog of quark-gluon plasma, but it does not exactly match with that, because string theory also assumes other ingredients. For example, it assumes that it needs supersymmetry. It demands supersymmetry to be present. Supersymmetry is basically a set of, I mean, again, I'm giving a heuristic answer. It basically predicts a pair, okay, the corresponding to electron, there is something called a super partner, all right, and the corresponding to every fundamental particle, there is a super partner, which we have not observed, all right. Given that ingredient added in to string theory, we have an analog of what happens in string theory, which is like a quark-gluon plasma, but it is not exactly the quark-gluon plasma that QCD predicts. There are qualitative similarities, but it is not exact match. Yeah.
Okay, few questions coming up. I will take quickly.
Yeah.
Fluctuations in the free space does have mathematical proof, and two is that in QFT, problem and concepts are in which space, like GR can work out in space time.
Um, I I understand the first question, but the second question I'm a bit confused. Actually, I'm not
Yeah, I
following the
am
question.
also not clear with the second question.
Maybe it can be rephrased, but I can actually answer the first question. Is that fluctuations in free space does have mathematical proof? Yes, there is mathematical proof. Yes. So you take a quantum field, and then basically you take okay, to simplify things, uh, take a scalar field, elevate it to the level of an operator, apply the rules of quantum mechanics to it, and then you will see that it has fluctuations associated with it, which is of course protected by the uncertainty principle. I mean, you don't see those fluctuations. That is true, but the fluctuations are there.
Fire Phoenix have got a question, sir. Can you elaborate on de Sitter space and how does its behavior influence quantum field theory?
Okay, so the de Sitter space is basically a kind of a space-time that you get when you solve Einstein's field equation, but an added ingredient that you add, it's called the cosmological constant, and you add a positive cosmological constant, okay? And then if you solve Einstein's field equation, you actually get a space-time which we call the de Sitter space, all right? So certain properties of it is basically that it's a maximally symmetric space. Maximally symmetric space means uh, it has the same number of symmetries that Minkowski space. That means our usual 3+1 flat space, the number of symmetries that this flat space has, the same number of symmetries de Sitter space has. In fact, the other way around, I mean, the negative cosmological constant, which is anti-de Sitter space, that is also a maximally symmetric space. So this trio of Minkowski space, de Sitter space, anti-de Sitter space are very special. Okay. Now, in the case of de Sitter space, there's a problem. The problem, I mean, it's not a problem per se, but formulating QFT in de Sitter space is non-trivial. Okay, it's different. The reason why is that QFT, works best mathematically. That means it's formulated best when you have time translation symmetry. Okay, that means you can go in time, go back in time, and space time does not change, the physics does not change. Okay, uh, so you can define a lot of other physical quantities like energy. You can do statistical mechanics with it and all of that. Okay, but in de Sitter space, you do not have this concept of time translation symmetry. Okay, and because of that, defining a lot of quantities like energy or mass, okay, in de Sitter space is slightly non-trivial, and therefore quantum field theory in the background of de Sitter space has a lot of open-ended questions. Okay, I can go into more detail of it, but that's fairly technical. Yeah. For example, I mean, to give you an example, you do not have a unique vacua. If you have if you consider a massless scalar field, massless quantum scalar field in de Sitter space, there is no unique vacuum. There are multiple vacua which are not equivalent to each other. They're all vacuum states. Okay, but so which vacuum to choose? All right, and depending upon the problem that you're trying to solve, one of them will work, one of them will not work. So that's there. Yeah,
Okay.
it's fairly complicated, yeah, in that sense.
Yeah. Okay. Mohit Chakra has got a question. When applying QFT to curved spacetimes, particle definitions become observer dependent. How fundamentally does our concept of vacuum state change when spacetime is no longer flat?
Okay, all right. So, unfortunately, the answer will happen to be slightly, let's see. So, uh, I'm just thinking how to put it in the right way so that maximum number of students can actually benefit from it. So, what do you mean by observer dependent? Okay, what do you mean by observer dependent? Is basically it means observer dependent means if I'm an observer, I have a quantum field around me, and I can define a vacuum state. Okay, there is another observer. He or she should also be able to define a vacuum state, and that should be possible. But problem arises if suppose what I call as a vacuum, the other person does not call it as a vacuum. So this is where the observer dependence comes in. Mathematically, what is happening is that the vacuum state, what do you mean by vacuum? The vacuum state basically means it's a state of zero energy because there is no particle. Okay, so let's back up a bit. What do you mean by energy? In quantum field theory, energy, or in quantum mechanics, energy corresponds to something called the Hamiltonian. Now, Hamiltonian happens to be the generator of time translation. Okay, just like momentum happens to be the generator of space translation, Hamiltonian happens to be the generator of time translation. Okay, so the observer dependence comes in if suppose my Hamiltonian is different from your Hamiltonian. All right, so the moment space-time is no longer flat, okay, then my Hamiltonian which generates time translation in my space-time, and the other observer for whom there is a different Hamiltonian, and that Hamiltonian generates time translation for that observer. If they do not match, then it becomes observer dependent. Then the vacuum structure itself is not equivalent. Means what I call as a vacuum, that person will not call it as a vacuum. The reason is because of the fact that he's using a different Hamiltonian. He or she is using a different Hamiltonian. I have a different Hamiltonian. And corresponding Hamiltonian, they define the vacuum structure. Okay. And the simplest of example is that if I uniformly accelerate with respect to suppose an inertial observer, my Hamiltonian will be different as compared to that person's Hamiltonian. And therefore the vacuum structure will be different. And therefore the definition of a particle itself is different. Because the definition of a particle in quantum field theory is excitation over the vacuum state. So if I have a vacuum state, on top of this vacuum state, if I have an excitation, that I interpret as a particle. And the vacuum state is basically it depends on the Hamiltonian. Yeah.
Thank you. That was wonderful. I mean, it's a very deep and very, very fundamental. I mean, to say you answered. So, wonderful. Okay. Next question coming up is that, sir, when we say AGI can solve QG, so my question is if it achieves AGI, then cutting data, and if we give it to UV catastrophe, then could it solve independently but by not using available data?
Okay. Uh, Let me try to see if I understood this question. So AGI is, I think, artificial general intelligence. Is that right? AGI?
Yeah, absolutely.
Yeah. So if artificial general intelligence can solve quantum gravity, okay. So what do you mean by solving quantum gravity? So there are many approaches to. Okay. This is okay. All right. So so there are many approaches to quantum gravity. Okay, string theory happens to be one of them. All right, and in string theory there is no UV catastrophe. Okay, just like I mentioned earlier that you do not need an ultraviolet cutoff when actually you look at interactions in the framework of string theory. But suppose there is some other theory which is not a string theory. Okay, it's not string theory, and but it's still consistent, and it is an approach to quantum gravity, and it does require ultraviolet cutoff and all of that. And if tomorrow AI can solve that and it can make that theory UV complete, ultraviolet complete. I don't know. I mean, whether it's possible or not possible, again, we don't know. Whether it's impossible, probably not. Probably not. But yeah, it's possible. And it also, what you call, okay, I'll come back to this. I'm not going to make that comment right now because somebody asked me about Swampland or something like that. Okay. So, yeah, there are multiple approaches to quantum gravity. String theory is one of them. And there are other approaches which is not necessarily consistent with string theory, but they seem consistent mathematically. Okay. So Swampland is connected with that, but I would not like to comment on that right now. But yeah, let's proceed.
Okay, this is a slightly different kind of a question. Cipher singularity is telling, I read somewhere Einstein himself said that the reality in its most fundamental form is not mathematical, even after developing rigorous mathematics in GR, but it is something else. Please put some light.
Well, I don't. So he mentioned. I have not come across this quote. Okay, but if it's he has mentioned it is something else. Unless I know what he meant by that something else, I can't even comment. Okay, what exactly is that something else? I can't comment on that.
Right, absolutely. Okay.
Yeah. I'm sorry. I can't
not
answer
a problem. Not a problem. Fire Felix is asking, sir, how can we relate open quantum field system with Markovian approximation?
Well, I only know open quantum field systems. Okay, I don't know Markovian approximation. I'm sorry, I don't know the answer to that. So what is it? If you can tell me what is Markovian approximation, maybe I can relate. Open quantum system is a very old subject. I mean, it dates back to Feynman. Feynman also worked on open quantum systems. Okay, but I don't know what is Markovian approximation. If you can tell me what is Markovian approximation, maybe I can.
Yeah, you can put it up in the comment. In the meantime, we will cover up it. Okay, Muzammil Akhtar is telling, sir, could you please explain cosmological constant problem and why is it so small?
We don't know the answer to that. Nobody knows the answer to that. But it turns out to be small. And in fact, the fact that it is very, very small explains a lot of our observations. But why is it small? Why it had to be small? Whether it was fine-tuned to be small, that's an open question. I don't think there is an answer to that right now.
Okay. Raghav Manchanda, this is again a different kind of a question. What is consciousness according to Roger Penrose physics theory, and what is your view on their theory?
Okay. Honestly, again, I don't think I can satisfactorily comment on this. I know that Sir Roger Penrose has this viewpoint that consciousness is intimately connected with gravity. That means gravity requires consciousness, and it's also connected very deeply with so-called the collapse of the wave function or the reality that we observe. Okay, but it's hotly debated, and still mainstream physicists do not take it very seriously. Okay, I'm not saying that it's wrong or incorrect, but somehow it has not found a lot of traction.
It is mostly philosophical and still on a very superficial
it's
level.
It's more of philosophical. Right now it's more at a philosophical level, and obviously since it's a Roger Penrose, it cannot be completely disregarded also. But again, it's going into a realm where, at least at my level, I cannot comment on it. Okay. So, but yes, he has. There are these books. I don't know. I had read them long time back. I mean, I'm talking close to like 15, 16 years back. There is two books:
Shadows of Mind and
Shadows of
Emperor's
the
New
Mind and
Mind.
Emperor's New Mind, Emperor's New
Yeah,
Clothes, or
yeah.
something like that. Yeah.
Emperor's New
So
Mind. Yeah.
yes, Emperor's New Mind. In those books, especially Shadows of the Mind, he speaks a lot about why gravity is actually necessary to what you call have a complete theory of everything. And in fact, he says that gravity is necessary. Without gravity, you cannot have a complete theory. And he also claims that consciousness, or what we call about observation or measurement problem in quantum mechanics, consciousness and gravity is intimately related. Without gravity, you cannot have a collapse. That's what he claims in that book. Okay. But again, I'm not an expert. I mean, I don't know who is an expert on this field right now, other than Sir Roger Penrose. But yeah, there are those claims, but I don't know. I mean, I'm not sure.
Right. Yeah. We are coming to the close of today's session. So, quick questions for Sir. Can we mathematically prove that a four-dimensional interacting Young-Mills quantum field theory exists and has a non-zero mass gap?
That's a millennial. If I know this, this is an unanswered question. I think there's $1 million prize for this. It's an unanswered question.
Okay.
Yeah.
Yeah.
To
Okay.
prove this, basically, to prove this.
To prove
Yeah.
this. Yeah. Yeah.
Yes.
So, Professor, after studying and working so much work on quantum field theory, what is your intuition about it? Is it the only fundamental field or some more fundamental field than QFT is there available in the universe?
It's not complete for sure. So my intuition right now tells you that it's not complete. It's definitely not complete. I mean, it cannot be the ultimate theory of a universe. But what would be the ultimate theory of a universe? That also is not completely clear. We have tantalizing clues coming from many other theories, including loop quantum gravity or even string theory. All right, which actually tells you that QFT does appear or does emerge as some kind of a low energy theory, low energy effective theory. Okay, but what the fundamental theory is, that is still an open question. We don't know the answer to that. It depends on who you ask. Suppose, for example, if you ask Leonard Susskind, he will say that the fundamental starting point of the building blocks should be something called D brains. Okay, D0 brains to be precise, D0 brains, and then something called the 5 brain or something like that. Okay, he starts with that and says that, in fact, he says that he does not believe in starting with a Lagrangian or a Hamiltonian and then applying a quantum rule to that. He does not believe in that either. Okay. It depends on whom you ask this question. If you ask Edward Witten about this question, then he will say that, no, let's actually reframe the whole of mathematics. He will say that let's go back to Langland's program and then let's see what Langland's program has to say about the geometric structures that emerge out of it. Okay. So it depends. But I can tell you for sure, and this is a unified consensus, that QFT in its present form cannot be the ultimate framework. That's for sure.
Hi, Professor. My name is Matthews. I'm a physics graduate student here in Brazil. My question is about effective field theory. What is your opinion on it?
In fact, what we deal with in general are effective field theories. Okay, and in fact, they're extremely useful, well understood in various. For example, you can have effective field theories of what you call even at the level of say, quantum chromodynamics, and they're extremely useful in predicting what you call behavior of physical systems that otherwise would be very difficult. I mean, the framework of effective field theory, since you're a graduate student, you'd probably understand the Wilsonian approach to effective field theories. Okay, where you basically integrate out all your ignorance of the higher what you call excitation modes and all of that, and eventually you will end up with a theory which is like a classical theory. Okay, you do not have to do anything with it, but it looks very different from where you started from. Okay, but it already encodes the quantum effects of the high energy excitations. You have included all of that, and eventually you have ended up with something which is basically telling you that at the low energy scale, what is to be expected. Actually, what we deal with is effective field theories at all times. Yeah. For if you ask me, is QED a complete theory? No, it's not a complete theory. It's probably an effective field theory coming out of some fundamental theory, and I don't care what the fundamental theory is. Yeah.
Okay, so this is a question that what you think is quark-gluon plasma proof string theory going in right direction
I
indirectly
think.
as we can. I think you answered this
Yeah.
question. Yeah,
Yeah.
yeah,
Yeah.
yeah,
Yeah.
yeah. Sir, what I would like to ask lastly is that you worked with a lot of people who have won Nobel Prize, quite quite renowned in their different field. Now, as a matter of principle, when you are a professor and you have students with you, I understand that we learned enough of the technical stuffs. Now, when we talk of making a career or focusing something, knowledge, success in terms of, say, for example, physics, your experience working in US, Arizona, then back in India, a lot of Nobel laureates, what would you, I mean, it is difficult, but still I would like to ask you, what would you suggest or give any suggestion, because you have worked with pioneers who have succeeded? Is it focus? Is it that distractions from social media, which I also find my students to be? Is it that studying for what I particularly find missing is that sitting down with a problem for at least 4 or 5 hours in at a stretch and then not concentrating on something else. Overall, what could be the strategy for success, if you can just, because you have worked with many people and you can even give some examples of the finer moments in your life when you saw something and got surprised that, okay, so even people can do this. If you can just frame something very interesting for us.
Okay. So actually, you gave the answer. I mean, one has to, if you love the subject a lot, okay, you really really love the subject a lot. Uh, on top of that, you need to have the discipline also. Okay, discipline. That means as a person, you are disciplined. You can regiment yourself. You can command yourself. Basically, that's the right word. You have to command yourself. Okay, and if you can command yourself and you can obey your command, you're regimented, disciplined, and on top of that, if you love the subject a lot, this is basically the ingredients for success, at least in my what you call field. That's what I've seen. I mean, you should be able to, like, okay, from my personal experience, suppose I'm dealing with a calculation which is very difficult. I know that it's very difficult. Okay, then you need to ask only one question: can this be done? If the answer is yes, then you should tell yourself that you have to do it. There is no other choice, but you have to do it. Don't give yourself any other choice. You say, I have to do this. For example, if you pick a textbook of quantum field theory or string theory and it seems incredibly complicated, you ask yourself, is this humanly comprehensible? The answer is yes. Humans have created it and it's humanly comprehensible. Do you love it? Yes, I love it. Then you have to tell yourself, then come what may, it may take me a long time, but I am going to understand this no matter what. I'm going to put in whatever it takes to get this done. I have to get this done. I mean, you need to have that drive. You absolutely need to have that drive. You cannot say to yourself that it's very difficult, I'm not smart enough. Yeah, you may not be smart enough as some other person is. Take more time, that's okay, but it's not impossible. And in physics research, that's what matters. It does not matter whether you can understand this in 2 days or 3 days. What matters is that you understand it. Eventually, take 1 week, 10 days, 1 month, but you understand it. You do it for yourself. And it is possible to do it for yourself. That's what I've understood. Uh, I mean, I've learned a lot from my advisor, Maulik Parikh also. I've seen him work. I've seen him operate. I've also, what you call, seen others operate. Like, for example, I also have seen Paul Davies operate, with whom I worked on, like, as you mentioned, side project of quantum mechanics. So I have worked with Paul Davies also. They have different styles of working. But one thing that is very consistent is that they don't just give up. They don't give up. I mean, there's nothing like going back. You may be stuck there, but you don't go back, right? You stuck there. You keep at it, keep at it, keep at it. Eventually, you will make incremental progress. Yes, sometimes you will make fast progress, but most of the times you will make incremental progress. But it is okay. Keep at it. Just keep at it. That's very, very necessary. Absolutely necessary. And this whole point of keeping at it, it's not just limited to physics. In today's world, it is necessary, period. If you do not want to be what you call obsolete in the face of AI, okay, then you have to keep upgrading your skills at all times. You just cannot give up. You cannot say that I will never understand this. You have to keep upgrading your skills. I'm not saying you have to learn AI, but basically, whatever you are doing, you become better at it. You become irreplaceable, is what I'm saying. And for that to happen, you cannot give up at any point of time. You just have to you try learning new subjects, try improving yourself, but never give up. Just don't give up. That's it. Tomorrow you may not be even doing physics. You may have to go to some other job. But there also, you have to keep pushing. So I have not, and I've never come across anybody who is successful, anybody in any field, say it be Frank Wilczek or Einstein or anybody, or Feynman or any, they have all been extremely hard workers. Hours and hours and hours and hours. But one crucial thing is that don't try to learn wrong things. That is a very, very, what you call, if you're unlucky, you will come across a lot of wrong things, and they will get inside your head, and they'll try to, what you call, condition you. And unlearning that is much more difficult than learning something which is new. So that is something which is you have to be careful about. Don't in the pursuit of knowledge, go slow, but don't learn something which is not right. Yeah.
Long hours of study, absolute concentration, cutting off from distraction, these are mandatory. I mean to say, with Nobel laureates and over your years of experience, you have found the same thing.
Yeah, this is consistent. Absolutely. See, it is not possible in the current age to completely cut out distractions, because distractions have become part of our lifestyle. Okay. But one should always be conscious about the fact that if I have to succeed in something, I eventually have to put in the hard work. And when I'm putting in the hard work, there cannot be any scope for distraction, at least during the time I'm putting in that hard work. If I set myself that I have to give these 2 hours to studying some new topic, or I have to understand this calculation, during those 2 hours, unless it's absolutely necessary, just cut out all distractions. And this is more so crucial for the students, graduate students, undergrads. Just cut out all distractions for that particular time. You can go back to your social media, go back to playing, go back to doing anything. Okay, go watch movies, go do whatever. But during that time, nothing, absolutely nothing. That is what I can tell you.
Thank you very much. Before we close, sir, just 2 quick questions coming up. Professor, I heard something as complex mass in QFT. What is its significance? How you can explain imaginary mass?
I have not come across it actually. Maybe in some other context, but in something, but no, not in standard QFT. There is nothing like that.
Sorry, going out of physics, but I want to know your viewpoint. Is it not possible to become polymath in today's time, like someone who wants to work in mathematics, sociophysics, pharmacometrics?
Is it possible? Yes, it's definitely possible. Whether it is practically what you call feasible, that's a different question. Given the kind of lifestyle that we have, the kind of stresses that we have, it's less probable, is what I would say. But Possible, definitely, yes. In fact, all of us always try to be polymaths, right? I mean, I love physics. I also love mathematics. I also like to do. I also have other hobbies. I like to pursue other what you call interests, but the time is limited, and it's a fast-paced life. It's so fast-paced. All your career progressions depend on very small niche of what you call parameters. So it is very natural, humanly natural, that you will focus on only those things where you will progress faster in your career. Okay, but is it possible? Yes, and try, see where you end up with. Yeah.
Okay, here is a question coming up from. Would Professor Samantray like to share some of the happiest moments of his life in the context of physics? Any particular concept or calculation or research that made him happy and thrilled?
Okay. All right. So there were two moments actually in my entire life which actually made me absolutely thrilled, and the first moment was when I was defending my PhD thesis. Okay, and when I was defending my PhD thesis, so the format in the US is that you will present your thesis to the committee, and then the committee will basically open up the questions to the audience, and after that the audience is asked to leave the hall. Only the committee will ask you the questions. Then that also has two portions to it. Okay, the first portion is that the committee will ask you questions only about your thesis. That's fairly standard. I mean, they will be very tough, they will be very hard, but it's okay. I mean, that everybody has to go through that. But the second part of it is that they can ask you question not from your thesis. They can ask you question from anything related to your expertise, but it will not be related to your thesis. Okay. So there was one question which was asked by Professor Paul Davies. Okay. And what he asked me is that, can you tell me the number of microstates of our universe? And that was not related. I mean, my thesis was about ADS, CFT, correspondence, and string theory. So after the whole thing was done, he asked me this question: Prashant, can you tell me how many degrees of freedom or how many microstates does our universe have? And I took a couple of minutes, but I did answer that question. I'll tell you what the answer is. Okay, so I was stunned for a couple of minutes, but then gathered myself, because at that time you are already very stressed out. And then I asked him, in order to answer this question, I need to know the value of the cosmological constant. And then he said that, all right, take the cosmological constant value to be something like 10 to the power whatever, something like this, minus 120 or something like that. And then I told him that let's assume that our space-time is de Sitter. It is not actually, but that's a fair assumption that it's de Sitter. And then the fact that de Sitter space has an entropy associated with that, and it is the entropy, again, just like any standard what you call general relativity and quantum field theory calculation, the entropy of a space-time will go as area of the boundary. Okay, in this case, the de Sitter horizon. So, and that de Sitter horizon is characterized by the cosmological constant. I mean, it's related to the cosmological constant. So if you know the cosmological constant, I can tell you the entropy of the de Sitter space. And once you know the entropy of the de Sitter space, it is related, I mean, through statistical mechanics, to the logarithm of the number of microstates, or the logarithm of the degrees of freedom. So you exponentiate the entropy, and that gives you the order of magnitude of the number of microstates of our universe, roughly speaking. I gave him this answer, and he was extremely satisfied by that. And I was also extremely satisfied with. So I would say that movement, not defending my thesis per se, or not being able to answer what I did during my PhD, but something which was slightly off, and I could gather myself and answer this question, that somehow gave me a lot of thrill. That was one instant. The other instant was when actually I published my first single author paper. Okay, that was way back in 2016. And that was a calculation I always wanted to do, and I was not getting time to do that. And I did that. It was basically about particle production in de Sitter as well as anti-de Sitter space-time. And I did that calculation, and I could relate that calculation. It was a cute calculation, and I could relate that calculation with something called the Unruh effect. Okay, Unruh effect is basically very closely related to Hawking effect. Okay, in black holes. So I could relate that to, and using the Unruh effect, I could derive particle production rate, or the rate at which a quantum field produces particles in de Sitter space or anti-de Sitter space. And when that got published, I was extremely satisfied, extremely happy. So those were the two moments in my research career which gave me a lot of thrill and happiness.
Thank you for sharing that. Astrotic is asking, I read your 2021 paper on Schwinger effect on compact space. So how do we know the imaginary effective action really corresponds to physical particle production to compact space-time?
Okay, I'll give you a very quick answer actually. So in order to do this computation of what you call particle production and all of that, you have to compute something called the path integral. Okay, so when you compute the path integral, what you actually get is something called the partition function. Okay, partition function in quantum field theory, or the generating function in the quantum field theory. So that is basically interpreted as a vacuum to vacuum. I mean, it starts from vacuum state, particle gets produced and goes back into vacuum state. So overall there is nothing. It's completely like zero particles. Okay, but when this quantity, which is basically like interpreted as from vacuum to vacuum, okay, the modulus square, sorry, the magnitude square of this quantity is interpreted as vacuum to vacuum. And when this quantity actually has some form like exponent to the power something real plus what you call imaginary times something. So in the exponent, there is a complex number sitting. And if you take the magnitude square of that, that is not going to be 1. It is going to be something which is not 1. It is going to be some number. So this vacuum to vacuum probability that this happened is interpreted as particle production. In quantum field theory, this is interpreted as particle production. If it is not 1, it is interpreted as rate at which you produce particles. So I computed that quantity basically in compact space-times.
Okay. Vishnu is asking, I am an ECE student. Does QFT have any application in electronics?
Not directly, no.
Okay. Abhijit is telling, sir, I am pursuing MSAI from IIT, sir, but my motivation is physics. Can I switch to physics? Sir, how many years it takes for me to settle?
You have to define what do you mean by settle. So if you're asking how many years it takes to do a PhD, 6 years, 5 to 6 years, depends again on the field, depends on your problem that you're working in, depends on your advisor's vision. So there are a lot of factors. But if you're asking me, getting a job, well, post your undergrad, you have to do a master's, then a PhD. Overall, probably it's going to take like, if you're going to do a separate master's, it's going to take you 2 more years, plus a PhD, 5 to 6 years. Then probably a few postdoc experiences, like for 2 to 3 years, ideally speaking, or maybe 4 to 5 years. Not, I would recommend don't do postdoc, like postdoctoral experience beyond 5 years. Don't do that. Okay, try to get a job before that, and so you can do the math. So if you start at the age of 21 after undergrad or 22, you can add up all those years, and we are looking at 32 or 33 or 34 maybe. Yeah. That's. Let me tell you this. This is a very, very idealistic and this is the fastest that it can happen. Okay. In general, you're looking at 35. Let me put it very bluntly. Okay. You're looking at 35, not less than that. Only if you're very, very lucky, extremely lucky, then maybe 30 to 33. But otherwise, we are looking at 35 and plus. Yeah.
Raghav is asking, sir, can you please suggest me a book on, sir, please suggest a good book for string theory.
What's your background? It depends on that. If you know quantum field theory very, very well, then there's the other books. I mean, you need to know quantum field theory very well before you can jump into string theory.
Okay. Astro, sir, you are researching on quantum gravity in Rindler space. Can you tell us about that?
Yeah. I mean, Rindler space as in Rindler, what you call Rindler space, Rindler horizons in anti-de Sitter space. That's what my specialization is. In fact, that's what my PhD thesis was about. So I was looking at what you call information loss paradox, but I was looking at a very special kind of a space time, which is called the anti-de Sitter space. And I was looking at the Rindler horizon in anti-de Sitter space. And I was asking myself the question that suppose you throw something towards this horizon, uh, do I have any remnant or any information about this fact that something actually fell inside the horizon? The answer to that comes out to be that yes, partially the information is encoded, and it is encoded in a very, I'm talking about my research during my PhD. Okay, that's what I did during that time. Now, of course, the field has progressed much, much, much ahead, and I don't work on that particular field anymore in that context. But yes, there's a lot of research on quantum gravity in Rindler space. Yes, I did it during a long time back, and that's the question I answered. That yes, it's possible. It's possible to get partial information at least. Yes.
The last question, and we will close that. Raghav is asking, sir, what is renormalization in quantum field theory and quantum gravity? If you can please explain both questions.
First thing is that in quantum gravity, it depends. What theory are you looking at as quantum gravity? If it is string theory, you don't need renormalization. As I said, you do not need an ultraviolet cutoff in string theory. So that is done. Okay. And about other theories of quantum gravity, I'm not an expert on it. I don't know how, loop quantum gravity deals with infinities or divergences. Okay, I'm not an expert on that, so I would not like to comment on that. But as far as quantum field theory goes, briefly speaking, renormalization is basically redefinition of the parameters of your theory. See, I'll tell you one thing. In quantum field theory, you start with something called a Lagrangian density, okay, where there are certain parameters like mass, coupling constant, and all of that. That's at the level of Lagrangian, okay. Then what you do is that you use the rules of quantum mechanics depending upon your taste, whether you can use canonical quantization or the path integral quantization to compute scattering, cross sections, and all of that. And when you do that, you encounter a lot of divergences, and then you renormalize, okay. But the heart of renormalization is basically, I mean, I'm not talking about, I will not go about the what you call conceptual approach of the Wilsonian renormalization, which is there, but I will connect it to that. I mean, it connects to what I'm going to say is that the parameters that you see at the level of Lagrangian, they are not observables. So the mass, the symbol m that you put at the level of Lagrangian, that is not the physical mass of the particles, or the coupling constant lambda that you put at the level of Lagrangian when you start the theory, that is not something observable. Okay, there is something called observable mass, there is something called observable coupling constant, and in order to get that, you basically redefine those quantities while you calculate those objects. And renormalization is basically that you adjust, or you reinterpret all those quantities at the level of Lagrangian, such that the observable mass or observable coupling constant, they come out to be completely finite. Okay, that is essentially renormalization. That do not interpret the parameters occurring in Lagrangian as physical parameters. They are not. What are physical parameters? They are basically connected to what appear as parameters in the Lagrangian, but in a non-trivial way. Okay. That's about it. I mean, that's about it. But if you want to, if you ask me mathematically, what is it? Yeah, there are techniques to do it. I mean, I can place a cutoff when I'm integrating. I will not go all the way to infinity, but that's not the modern way to look at it. The modern way to look at it is basically dimensional regularization. Okay, that's fairly advanced. I mean, if I tell you, you'll get more confused right now, but it's a legitimate technique.
Sir, as a renowned QFT researcher, how do you personally view Ant-Man's idea of shrinking to the quantum scale? Is there any interesting connection to real quantum field theory, or is it fundamental imposition?
I don't know what is Ant-Man's idea of shrinking to quantum
Yeah,
scale.
I am also not very clear. Okay. So,
Yeah.
sir, thank you very much for this. I know it has been very extensive. I would just like to bring forward few of the comments. Thank you very much, sir. That was an incredibly brilliant and insightful explanation. The way you mapped out the concepts made the physics so much clearer and absolutely fascinating. This is one comment which has come up. Jahangir is telling, amazing teaching method and love you, sir. Raghav Manchanda is telling, sir, thank you very much. From my end, sir, I really have no words to thank you. And I think you really enjoyed today's podcast because a lot of questions, etc., came up. And thank you for all the viewers who have really joined to make this podcast enriching. So, with this closed note, sir, I think that as a senior researcher, I think you would lay out a very promising future, isn't it, for the people who wants to take up research in quantum field theory in India, as far as it is concerned.
Yeah, I mean, I would like to thank you, Dr. Shaunak, for giving me this opportunity to have this wonderful session, and I'm so happy, and I'm so what you call excited to see the kind of questions that students were asking. I mean, absolutely brilliant, and the interest in the subject fantastic, and I enjoyed interacting with all of you, and brilliant set of questions. And thanks again for this wonderful session. And uh, please, I mean, the series that you have, like for students, it's a great initiative, and I'm sure this will grow leaps and bounds, and you will get many more what you call researchers speaking on your
Yeah,
podcast.
yeah,
I
yeah.
wish you all the very best, and
Thank you very much. It
I
is a
hope this
blessing for
becomes
me.
really, really big, your podcast, and yeah, best of luck
Yeah,
for
only,
that.
yeah. Only thing is that because the number of subscribers are very limited compared to the very popular people who are doing science. Because
Yeah.
my channel and the people who come, as you understand, is very serious. More than 2 hours you are talking just out of my request. So I mean to say, these are people we have got. I have got limited people, very very intelligent people. But anyway, sir, thank you very much. Do not disconnect. I will just have take 1 minute of your time, and
All
then
right.
we will find interest. Somebody is telling, sir, हम भी morning से wait कर रहे थे कब आपसे interact करें.
That is so sweet of you. Thank you
Yeah,
very much. I appreciate
I
it.
got
Yeah.
so I got a lot of WhatsApp coming in, Messenger coming in Facebook people are writing, LinkedIn I posted, and many people were telling that we are really waiting. So when are you coming up? I told them you need to wait. It is scheduled already, and as you understand that money for this point of a channel and talk, it is nothing, because the love that I get from my subscribers, the love that and excitement, it keeps me pushing on. And they are now connected. I've created a WhatsApp group, etc. Okay, quickly, just a reminder, Raghav, if you want to join the 27th September webinar, just give me a WhatsApp message and I will tell you what are the things that you need to do. My number is 98302196777. So thank you very much. I mean to say, it has been great, and thank you very much for coming and taking a lot of time. So be there just for a minute. And thank you for all the viewers wishing to continue this podcast episodes in the near future. Thank you very much for joining.
Thank you. Thank you very much to all. Thank you very much to all. It's a pleasure. Yeah.